Dear friends, many of you who are watching this channel very carefully would be following this course on advanced convex optimization might have thought that I have stopped doing that particular stuff, but no, this is very close to my heart and this whole course will go through. So today we are going to discuss a very important thing, complexity of subgradient methods. So we'll take one particular subgradient method which will be useful for polyhedral functions, in the sense that minimizing polyhedral functions whose epigraphs are polyhedral or which can be expressed as a maximum of finite number of affine functions. And we will show that for such cases we can actually reach an approximate solution quite fast if we choose our step sizes carefully. And that is what is called the complexity, the iteration complexity, the number of steps required to reach approximate optimality. And that's what is our key discussion here. We are not going to discuss too much about proofs. Those who want to know the proofs can get into my website at IIT Kanpur, get my email ID and email me. I'll send you the write-up. I thank Dr. Tanushree Pandit, my former PhD student, for a very excellent discussion with me, which enhanced the quality of these notes. And obviously Ketan Atul Bapat, PhD student in electrical from IIT Kharagpur, who is actually typing the notes. I am really grateful to both of you. Our concern, as always, like the previous lectures, is like lecture 5, is a minimization of a convex function f, which is defined from Rn to R, to minimize it over the whole of Rn. That is, we have an unconstant minimization problem. We'll assume that their minimizer exists. The set of minimizers is non-empty, which is given by this equation 6.1, telling that argmin of f is it should not be fx, it should be f is not equal to 5. Our concern here is about an approximate minimizer. So given a threshold epsilon greater than 0, which is very small usually, a vector x is called an epsilon minimizer over the whole of Rn if f of x is less than or equal to f star, where f star is the minimum value of the function. That is, for any x star in the argmin set, f star is f of x star, right? That's the global minimum value. So f of x must be less than f star plus epsilon. So what you can write, you can also say the definition is same as writing f of x is less than or equal to f of y plus epsilon for any y in Rn. Once we have done that, we will move to a very important condition which would be used here in the algorithm. And this condition is a key to what we will do. And that is why we will say that this immediately restricts possibly the class of convex functions which we can minimize by this approach, and for which a so-called complexity theory, where we will talk about polynomial time algorithms and all stuff, are really useful, are valid. So here we call it the subgradient assumption. As you know that we are not assuming differentiability, but because the function is from Rn to Rn, the subgradient is non-empty at every place. Most places it has the gradient, but some places it doesn't. Okay. So what it says that let there be an L, a fixed L, such that for any x that you take in Rn, and you take a subgradient of f at that x, so v is element of del fx, norm v would always be less than L. It doesn't matter what x you choose, L is independent of the choice of your x. That's the first step that you should know. An example which happens, for which you can calculate, is del of fx, for which the subdifferential, as you know, can be written like this: x sub 0 all points has the derivative, which are minus 1 and plus 1, and x is strictly bigger than 0 and x is strictly less than 0, and at 0 it is minus 1 plus 1, that interval is a subdifferential. So if you look at this function, you will know that this is nothing but max of x and minus x of two affine functions or two linear functions. So, and its graph is a polyhedral convex set. Its epigraph is a polyhedral convex set. So all functions, if you take the maximum of finite number of affine functions, then its graph would look like the polyhedral its epigraph would be a polyhedral set, and the function is called a polyhedral convex function. You can go to my first lecture, Invitation to Convex Optimization, and then you could see a kind of details about this thing. So if I assume that subgradient assumption, then we can prove that the function f itself is Lipschitz over whole of Rn. That is, the absolute value of fx minus fy is less than equal to L times the norm of x minus y. That is the meaning of Lipschitzianness. And this is true for any xy in Rn. So if you take the subgradient assumption, the one which we had just seen, that would guarantee that the convex function is Lipschitz over the whole Rn. We know convex function is locally Lipschitz, but this condition is equivalent actually to the fact that it is Lipschitz over whole Rn. And if a function is Lipschitz over whole Rn with the Lipschitz constant L, then the subgradient assumption holds with that same L. Now I am not going to give the proof here. As I said, that proofs would be for those who want to devour it themselves, because proofs have to be carefully read. So I would now skip over to our main algorithm. Then this algorithm first appeared in Nesterov in 2009, but I have written it slightly differently because I had done a more detailed kind of analysis so that students can be helped. You will observe here that we are not going to talk about anything about step length. So what we will consider, that we will consider a starting point, and we will at every xk step kth iterate when we get, will check whether 0 is in del fx. If it is not there, see, this is a very idealistic situation. I am checking 0 is in del fx. I might not be able to check. I might say that, okay, I take a very small alpha naught, very, very small quantity. If I can find a norm of psi k, which is less than alpha naught, I will say that, okay, we can take that point as a approx kind of a solution, right? But from an idealistic point of view, I should check check whether 0 is in del fx k or not. You might ask me, okay, then guy, this is not good. You have to know the whole subdifferential. Of course, these are the drawbacks of a method. See, once you want to know how interesting a method is, you should also know what are the drawbacks of the method. So in reality, you are not really going to make such a kind of check. Such a kind of check would be not made at all, right? Now, we would just keep on going, and when we will see that xk plus 1 doesn't change much from xk plus 2, so then we will kind of stop the algorithm. That kind of sort of thing, or the difference between xk and xk plus 1 is extremely small, and that kind of, those would be implementation strategies which one can take in practical situations. So what we do that, okay, if you have 0 in del fx, ideally you should stop the algorithm. If not, you carry out the iteration in a way such that x of k plus 1, that is the k plus 1th iteration, is xk minus lambda k into psi k, where lambda k is a step length and psi k is a subgradient of del fxk. And it is any subgradient, it is not a descent direction. So I am not expecting the function values to go down. So that is why these class of methods are called non-monotone methods. That is, we don't expect a decreasing function value. You might say that, oh, then what is the use? But the whole point is that even if you don't have a decreasing function value, as you have seen in section 5 or lecture 5, that we still can achieve something. We can still do certain things. Okay. Now let us look at this algorithm. After we have seen this algorithm, this result by Nesterov. See, please note that I am not going to talk about step length now. It will be chosen later on suitably based on the situations we have at hand. So let us consider this particular optimization problem where you minimize the same function f, but you are essentially getting a constant problem. You are trying to say that, okay, suppose I can solve this constant problem. You can say that, okay, guy, come on. You have to ask me to solve an unconstant problem, then you want to yourself solve a constant problem. What kind of stuff is this? Why do you do that? See, this f star d is something you do not really solve. You just really don't solve it. It is something you do not know. You're not even interested. You have to take d very, very large. See, what would happen if the function fx is a continuous function, and this what does x minus x naught whole square less than equal to 2d means? That x is an element of a closed ball centered at x naught and of radius root over 2d, which means it is a compact set and a continuous function, convex function on Rn is continuous, will have a minimizer. So this is valid. So I don't need know the value. I don't even need to know the value. What I need to know is the value of this f bar k, which is based on computing the function values up to the kth iterate starting from 0 to k, this k plus 1 iterates. Choosing D. Now what would happen? What is the idea here? The idea here is that actually in reality instead of f star D we'll have f star. But let us just look at this. We can prove that the difference between f star D and f bar k is not that we cannot estimate it. It cannot be larger than this quantity, where it is given in terms of the constant D which you have set here. The L square is of the subgradient, the L of the subgradient assumption, and these are the step lengths. Okay. Now this f bar k is nothing but a weighted average or a convex combination of the functional values that you have computed at each of these iterate x0, x1 dot 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 xk. Once you have done that, this is what you will get. So that is the first step. Now what we say is important is this result. Now suppose I choose D suitably large, or maybe if you are lucky suitably small. Okay, so if you choose suitably large, you will most probably have it. You choose it so suitably large that the ball centered at x naught, the starting solution, and having a radius root 2d, that ball would be so large that the part of the argmin set will intersect it, that it will get inside that argmin set. So there will be x star, an argmin means a solution or minimizer of the problem would lie inside that ball. So if x star is a minimizer of the whole f over Rn, then if I want to minimize the function f over that ball, that x star then has to also be the minimizer, because it is the unconstant minimizer. It has the lowest functional value for over whole Rn. So it is definitely has the lowest functional value over the ball. So choosing D sufficiently large, we can have this condition now. Once this condition is done, you might ask, okay, I would be interested in, suppose you stop at kth iteration and you said, okay, fine, this quantity has somehow become very small. I have chosen that this quantity, this summation I equal to 0 to k is growing rapidly, so maybe, and this I somehow suitably control, and so this thing becomes very small. And he said, okay, kth iteration is fine. So, but what is my output? I cannot say f of xk, I cannot say, okay, the function values have decreased and come up to fxk. So there are two ways of looking at the output. One is the construction of a point like x hat k, which is called kind of an ergodic sum. It's called a weighted average of the vectors, not weighted average of numbers, but weighted average of vectors. And if you look at this and you operate f on this weighted average, then what does it say? By convexity of f, because I can write this in this convex combination form, so by the convexity of f, this is equal to this, which is same as the weighted sum of the f xi's from 0 to k, and that is f bar k. So what you are showing through this application of convexity of the function f, that this ergodic sum, the functional value at this ergodic sum is less than f bar k. So if I look at this inequality 6.10, which you have to keep in mind, you may just, if I hold it for some time, those who are watching can just write this down, this inequality, 2d plus L square into summation I equal to 0 to k lambda I square divided by equal to 0 to k lambda I. Okay, fine. Now what does it say? That f of x hat k is less than f bar k. So f of x hat k minus f x star is this. So this is the inequality that what we possibly require. So x hat k is not the kth iteration. I have walked out from 0 to k, and then I have jumbled up those points into kind of weighted average, and that I take as my output. And then I have to say, does it make any meaning taking this output? That is the question. So then comes the question of convergence. Of course, another way of taking the output is that okay, you take the minimum value at the back. You might be hearing there is a railway line here where the trains pass pretty frequently. So maybe I'll wait a bit till the sound of the train passes. Otherwise, I'm sure it will catch it up. So another way of taking an output, which is the second output, is instead of taking this kind of ergodic sum, you just take the functional value, the minimum value of the function among them, and that is what you would put instead of f bar k, because you can prove that this is less than f bar k. So what we do now is that suppose I take f of x hat k, and I at every kth iteration I get this ergodic sum, then and compute the functional values at this point. Then does those functional values converge to f star? Then for some large k we can take this x hat k as a solution. That's the key idea. So then we take the standard step size rules. The sum of the infinite sum is divergent and the square sum is convergent. So square summability is there, but summability is not there. And then we can prove that f of x hat k goes to f star. In fact, f hat k also goes to f star as k tends to infinity. Whatever be your output, it just goes to f star finally. So this is called the Robbins-Monroe condition. Herbert Robbins is one of the greatest statisticians of the 20th century. Is one of the legends in mathematics, and a person whose life is nothing short of an adventure. Who in one of his interviews had made a comment like that. Somebody asked him that you, 65 years old, in the last 5 years you have written 18 papers, some of them are breakthroughs. How can you keep up with so much of work and so much of perseverance? He said that is the mistake you are making. You are looking at a 16-year-old boy in the garb of a 65-year-old man. That is the curiosity which should drive the life of research scientists. Then only you enjoy the subject. So I'm not proving it is very simple. It's just I'm knowing that this summation lambda I square being convergent, it simply means that the sequence of partial sum is convergent, and hence convergent sequences are bounded. So we'll take the bound, any partial sum is bounded by some given number which is fixed. For every partial sum would be bounded because the sequence is bounded, and just applying that and applying the divergence of this series you can just do it. That's it. Now it comes a very important thing called complexity analysis. So what is complexity analysis? Complexity analysis tells us that, look, guy, your job is not to bother much about convergence. In practice, your job is to reach epsilon-optimality as fast as possible. If you can reach in quite fast number of time, we will say you are doing something in polynomial time. If you keep on going for aeons, then we will say, okay, you are in exponential time. Aeons doesn't mean for ages. It could be few minutes or maybe 10 minutes, 20 minutes, or maybe huge number of iterations, exponential number of iterations. You call that, then you are doing things in exponential time. So what we are bothered about is iteration complexity. How much iterations you require? What is the minimum iterations you require so that you can get something like this? F of xn minus f star is less than epsilon. You need to find this n. Anything bigger than that n would be fine, but this n, the minimum number of iterations required to reach epsilon optimality, has to be known. There are other kinds of complexity like operational complexity, because these algorithms are called black box algorithms, because there is a black box. You are just putting x there and you expect the value of function value fx has to be known, and it will also throw you a subgradient of f at x. So how many calls you have to make to the black box in order to finally reach epsilon optimality. So there are several books I mentioned here where there's a discussion of this complexity in optimization algorithms. One book is Interior Polynomial Algorithms in Convex Optimization. If this might not look very easy for you, then look at the book by Stephen Wright, which I have not mentioned, but is possibly a good, it's a fantastic book. One of the optimization books I love. It's called The Primal Dual Methods in Optimization in Linear Programming. I will do something from that book, and the later stage when we are talking about structure optimization, Stephen Wright's book will play a major role in our study as we go through. Because the interior point is a revolution that has to be studied, right? But of course, I'm not going to get into the issues of Karmarkar algorithm and all. Okay, we will go do in some slightly different way. KKT conditions would guide us through. It's a matter of choice at the end. Now, what it says, what the algorithm that we had to know is the following. That, okay, suppose I take epsilon as a threshold. In my context, I am not interested in f of xn because it's a non-monotone algorithm. What I am interested in is using this inequality as my definition of epsilon optimality, that f bar n is the iteration number where you want to stop, minus f star is less than epsilon. That is my definition of epsilon optimality now. So I want to know the n, or the minimum number of n in which I will reach this condition, given me the epsilon. So I said, yes, you can do that. That for any n which is greater than this quantity, it can 2d by L square by epsilon square. So the minimum of this could be taken, the minimum n value could be taken as the ceiling function of this, provided lambda I is chosen as epsilon by L square over all the I starting from 0 to 1, 2, 3, 4, everything. Now, you might say that you have chosen a constant step size, but for convergence you cannot have constant step size. I agree, I have chosen it because I am not bothered about convergence at this moment. I am simply bothered about epsilon optimality. Now, I am not going to do the proof here. The proof is very simply stepwise written. When you have a situation like this, that the minimum step length is kind of constant into 1 by epsilon square, we call that the process or the algorithm has an iteration complexity of big O of 1 by epsilon square. So when you have a big O of some quantity, that is the threshold, big O of some power of the threshold, then we say that the problem actually works in polynomial time. So what happens if D is pretty large, L is not very large, epsilon is a suitably chosen quantity, then this is a number which is achievable. This number is easily achievable by an algorithm, this number of steps. It might not turn out to be very large either in reality. If epsilon is larger, obviously it wouldn't be larger. If epsilon is smaller, it would be more, right? Just by looking at the structure. Have a careful look. 2d L square by epsilon square. Now, first question is, how did you choose this? How did I choose this epsilon by L square? Where is the motivation? The motivation of doing so actually came from looking at in this recent book by Nestor of Convex lectures on convex optimization. I'll just show you that book as well as also Stephen Wright's book, which I mentioned here. Please have a look at this book. One of my favorite books in optimization. Very well written. Excellent, excellent, and excellent. And Stephen Wright is one of the legends of optimization. And this is the book by another legend, Uri-Nesterov. This is a very new book by Springer. Of course, I don't expect students to buy it. You should get it from the library. It's a pretty costly book from Springer by Uri-Nesterov. In page 202 and 203 of this book, I found Nesterov was trying to explain this issue of iteration complexity for projected gradient method, projected subgradient method. So I took that idea and built it for the system here. So I don't claim any originality here, but okay, that idea is modified for this situation. So of course you can ask me why I took epsilon by L square. All the lambda has been constant. I will show you here at the end that if I choose the one by which I obtain convergence, I might be in a problematic situation. So I skip over the proof. What I see here is the following. So you know f bar n minus f star from my corollary 6.6 would give me this one. Basically now I've divided by L square, both up and down. I'll call this part theta n because it depends on iteration number n. Now what do I have? F bar n minus f star is theta less than equal to theta n. Suppose n is so large that my theta n somehow is quite small, and I say okay, let theta n be my threshold, be equal to epsilon. Then immediately from this inequality I'll say that I have reached the epsilon optimality. So let us see. Now suppose I know that okay, if theta n is my epsilon, so at the nth step I have reached epsilon optimality. So what kind of step size would actually give me, what kind of step size would actually generate that thing, would actually give me this scenario, will actually allow me to really compute the step size by the iteration number, the n, capital N. So I now have to choose step lengths up to capital N only, because I know that at capital N I can stop because I've chosen theta n to be epsilon. So I'll choose lambda in this fashion, which is root over 2d by L square by root over n plus 1. This root over n plus 1 is a crucial thing. And this idea I've got from Nesterov's book, page number 203 in this book. Now theta n, when you compute, takes a form like this: L square into root 2d by L square divided by root n plus 1. If you observe the definition of lambda I, then you will immediately know that this part is lambda I. So it will be lambda I into L square. So theta n is lambda I into L square. But now we said okay, theta n is epsilon, so lambda I is epsilon by L square. So this is the motivation. Now, but this is a very special situation where I have taken theta n to be epsilon. But when I was doing the main theorem, I had not bothered about theta n being epsilon. I have not even written the term theta n. I just choose lambda is epsilon square and just have gone through it. So what I did in the theorem was I just took this whole thing and I just put lambda as epsilon by L square, did the computation and obtained something like this. Then in order to achieve my inequality, it will be sufficient if I have this part to be less than epsilon, and from there I obtain this inequality, the result. Now in this special situation, what happens is that okay, you put back in theta n structure lambda is equal to epsilon by L square. Once you do it, theta n becomes exactly equal to this, but theta n you have chosen to be epsilon. So once you put this equal to epsilon, it becomes, we conclude that n plus 1 is this. So when theta n is chosen to be epsilon, this 2d plus L square is actually a integer. 2d into L square divided by epsilon square is an integer, because then n, the number of steps, is nothing but 2d by L square epsilon square minus 1. That is n plus 1 is of the order of 1 by epsilon square. Okay. So in this situation, that 2d by L square by epsilon square is an integer, and it can, in this particular situation where theta n is equal to uh, epsilon, then 2d by L square by epsilon square minus 1 can be taken as an iteration count. But not in my theorem. That theorem doesn't tell me that 2d by L square by epsilon square would be integer. Then we take the ceiling function. Okay. So now you might be asking, so come on guy, what is the issue with you? You take something for convergence and you're taking constant step size for reaching epsilon optimality. What happens if you choose a step length for which the convergence occurs? See, the problem is that if you have something like this where you have divergence plus second square summability, you cannot choose constant step lengths. And then let me choose step lengths as lambda equal to 1 by 1 plus I plus 1, because I start with 0. So lambda 0 is 1 and lambda 1 is 1 half and something like that. So now if you look at summation I equal to 0 lambda I squared, this is actually the famous Euler's identity, which is equal to pi square by 6, Euler's infinite series. It is actually a Riemann zeta function, zeta 2, for all those who are affection or enthusiasts of the Riemann zeta function. So, and for students of optimization or convexity, the Riemann zeta function for a positive, for a real S and for positive S greater than 1 is a convex function. Now once you know that summation lambda I square is less than equal to pi square by 6. My lambda is chosen like this. So this is something for which convergence will occur. Convergence is guaranteed. But then when I look at this summation of lambda I and I look at its partial sums, usually in mathematical literature and analytic number theory and analysis, Hn is the nth order. So I shouldn't have written dot 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 this one. Sorry, is the nth order nth partial sum of the harmonic series, this 1 plus half plus dot 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 n. So basically nth Hn means you just sum up to 1 by n. So in our case we are having Hn plus 1 because we have n plus 1, 0 to n. So it is I equal to 0 to lambda I equal to 0 to 1 by 1 plus I. And we can prove that when you have n plus 1 terms, right, when you have n plus 1 terms, then h of n plus 1 is this. And then log n plus 1 is strictly less than hn plus 1. So difference between hn and log n actually decreases when n goes to infinity. They approach a fixed constant called the Euler's constant, which is has a symbol gamma, and it is not a very high number. So then if we write c is equal to this, a constant now, then theta n is actually c divided by ln plus 1, because 1 by hn plus 1 is strictly less than 1 by ln plus 1. So I am not putting strict, it should be strict inequality, but okay, doesn't matter much. Yeah. So if we set this to be less than epsilon, then we'll get theta into epsilon. I get n, that is n plus log of n plus 1 is equal to c by e, and hence n is strictly bigger than actually except e to the power c by e minus 1. It's a huge number of steps because c is large and epsilon is small, then c by e is large, and you have to keep on just doing things. Exponential number of steps are required. That is not true when you have taken a constant step size. So when you are implementing something so that you reach in less number of steps into epsilon optimality, that those step lengths may not be same as the one you needed for convergence. See, the issue of convergence here is that the problem here is that you have the lambda I square here, that you need to control somehow. That this part has to vanish, go towards infinity faster than this goes, then only we can have 0. Otherwise, it's not possible. So that may not be known beforehand. So some condition is imposed on lambda I square. So I hope this gives you a fairly compact idea of what's going on, and hope things are nice with you. Stay safe, be happy, and do comment, do have questions. If any expert in convex optimization, some of them are maybe my very close friends who would be seeing it, uh, you too do please comment. That would be a learning thing from me. I am largely been a theorist. My friend Regina Burachik first initiated me into this world, lovely world of optimization algorithm, and since then I've remained interested. And as a physicist, a very famous physicist, Leonard Susskind has said that in order to learn physics, you have to write about it. So, in order to learn convex optimization algorithms deeply, I need to write about it, and that's exactly what I'm doing. Uh, Thank you very much. Thank you once again. Have a good day.